Hey everybody, and welcome back to CSE 1322. This is going to be module number 7, and this week we're going to talk about threads. So the idea of threads is that sometimes you might want to be able to do more than one thing at a time on your computer. In modern computers, the CPU, or the central processing unit, which is where all of the work is done in your computer, typically have more than one core. When you purchased your computer, you might have bought a 2 core, a 4 core, an 8 core, 16 core processor. Likewise, even your phone today typically has multiple cores. Most programs that are written today are written in such a way that they are capable of using more than one core. But thus far, every program you've written has been what's called single threaded, meaning that there's only one execution path through the program. So, parallelism is about making it so that your code can take advantage of these cores and do more than one thing at a time. This is a huge topic, and in today's lecture, we're not going to be able to cover absolutely everything about this. Honestly, this is typically an entire college course because there's a lot of intricacies of being able to do multiple things at once. But we're going to scratch the surface and give you most of the high level ideas during this lecture. Okay, so let's take this example. Let's imagine that we want to write a quick text messaging app that allows people to send messages to each other. So you might have something that allows you to read from the network. We saw how to do that in the last lecture with sockets. And so effectively, it's going to wait for a message to come in on the network. It's then going to print whatever that message is, and then it's going to allow the user to type in their response, and it's going to send that out over the network to the destination. And so this is a pretty simple little app. Basically, it reads in a message from the remote side, and then the user types their response, they hit send, and life is good. So is this how real text messaging works? Are you only allowed to get one message before you must reply to that message? No, it's possible that you could get a message, another message, and another message, and then reply to the three. You don't necessarily do a one in, one out kind of deal. So this doesn't really work. And if you look at this code, if you were to implement this, it literally is going to wait until the user types in their reply before it possibly sends that over the network and before it would ever get the next message in. So this doesn't really work. And there's a lot of applications that are like this where you need to be doing two things at once. Effectively, what you need to do here is you need one thing that is constantly reading from the network and telling you any new messages that are coming in, and a second thing that allows you to send messages out. And those two things need to be able to work simultaneously. So, this is going to be a multi threaded application. One thread is going to handle the incoming messages, and a separate thread is going to handle the outgoing messages. And then both of those can run at the same time. This allows you to be typing a response at the same time that a message is coming in, which is how messaging apps work. All right, so this thread idea, a thread is basically an execution path through your code where one block of code is executed on one thread, and then a separate block of code is executed on a different thread. Up until now, every program that you've written has had a single thread, and that thread begins at the beginning of main and runs through main. And there is only one thing happening at any given time per Java program that you run. But if you want to be able to take advantage of the idea of having multiple cores where you could conceivably be doing more than one thing at a time, you need to write your code in such a way that it is capable of being multi-threaded. So, how do you do that? Well, in Java, there are two ways, but the way that we're going to cover is to implement the runnable interface. And in that case, you must have a class that has a run method that is actually going to be the code that you want to run. So, let's take an example. We're going to make a dog class. So, we have class dog, and it's going to implement this interface. So, remember that this is the syntax for implementing an interface. The interface is not one you wrote, it's one that's built into Java called runnable. So you're going to say class dog implements runnable. Okay, in here we have a static int dog counter just so we can keep track of our dogs, and we have a constructor that sets the ID of the dog to the dog counter and increments it and all that good stuff. So nothing here is thready. But then we have a method which has to be called run. So the rule of interfaces is that they have a list of methods that you have to implement. And in the case of runnable, it requires that you have a method called run, which takes no parameters and returns void. You can't have parameters, you can't return anything other than void. So you must have a public void run. Inside of that run, you put whatever code it is that you want this dog to do. So in this case, what the dog is going to do is it's going to move from position 0 to position 1000. So imagine a track, and the position just tells you where along the track it is, and the dog is running along the track or the sidewalk or whatever else. So all that's happening is it's just counting from 0 to 1000 and telling you the dog number, whatever dog number it is at position 0, 1, 2, 3, 4, 5. So if this was not implemented as a thread and you ran this, you would make an instance of dog. You'd say dog, my dog equals new dog, and then you'd say my dog dot run. It would simply say dog 0 is at 0, dog 0 is at 1, is at 2, is at 3, is at 4, is at 5, and it would count all the way up to 1000. But since I've written this so that it is threadable, I'm able to have more than one dog at a time. So what I'm going to do now in my main method is I'm going to say dog D1 is new dog and dog D2 is new dog. So I've made two instances of this dog class. And then I'm going to make a new object called thread, which you've not seen before. Thread T1 equals new thread. And in parentheses, I tell it this is going to handle dog 1. Thread T2 gets a new thread, and it's going to handle dog 2. So I've made two dogs, and now I've made two threads, and each thread is tied to one dog. And then finally, I'm going to say T1.start, T2.start. Now, this is a new syntax that you've not seen before, and there's something a little bit unique about this. Generally in Java, when you execute a line of code, it has to finish that line of code before it moves on to the next line of code. And so if you have something like a scanner.next line, it's going to sit there forever until you actually type something in on that scanner. But this t1.start is a little bit unique in that it begins running thread 1 and simultaneously it moves on to the next line. So, regardless of how long T1 takes to run, it will move on to the next line simultaneously. As a matter of fact, what happened here is right now we just made two dogs. Nothing magical has happened. That's normal code as if it had a single thread. And here we're just defining the threads. But at the moment that you run t1.start, there is one thread that's handling the main. That's the thread that is doing these lines of code. And at this line, we suddenly get a new thread that starts up that is now going to handle the run method in dog D1. And then it the main thread moves right on to the next line, which starts yet a third process or a third thread. It's not a third process that's going to handle dog D2. And now, at this moment in time, the main thread, the D1 thread, and the D2 thread are all running simultaneously. They're all executing their code at the same moment, at least in theory. There's a little bit of a caveat there. But the way you want to think about it is the moment you start a new thread, effectively there are now two, or however many we're up to, separate execution paths that are running simultaneously. All right, so if we were to look at the output here, we would see dog D1 is at 844, dog D1 is at 845, 846, 847, 848, 849. But then in the middle of this, we suddenly see dog 2 is now at 854, 855, 856, 857. So at the same moment that dog D1 is working through its loop, dog D2 is also running through its loop. And since the output can only show one thing at a time, we're actually going to see messages from D1 and D2 just kind of mixed together because they're both happening simultaneously, which is pretty cool. In this example, we're assuming that we're seeing a lot of D1 and then a lot of D2 and then a lot of D1. And that is actually what's probably going to happen most of the time for reasons that I'm going to explain here in just a second. Okay, so the order in which you see the output from the dogs is actually not predictable. I'm going to stop and say that again. The output that you're going to get is not predictable. You might see all of dog 1 and then see all of dog 2. You weirdly might see all of dog 2 and then see all of dog 1. Or you could see a bit of dog 1, then a bit of dog 2, then a bit of dog 1, then a bit of dog 2, and so on and so forth. And each time you run the program, it may actually give you different output. So, why is that? Well, it's because the scheduling of threads is done by your operating system. It's not something that you, the coder, have control over. In my case, I'm running this on a Windows machine, and so it's Windows who gets to decide which thread gets to run when. As a matter of fact, that is one of the core jobs of an operating system. So we're just going to take an aside here for a moment and we're just going to talk about what an operating system is. So you're used to the idea that somebody is running Windows, or maybe they're running Mac OS, or they're maybe running Linux, or if they're on a phone, they're on iOS or Android, most likely. And so, what actually is an operating system? You picture it as like the layout of the screen and how you interact with the start button or the finder or whatever else. Or in the case of a phone, it's how you touch items on the screen. And that's logically what you think of as the operating system. And that is definitely part of it. But a big part of the operating system, what it's really doing for you, is it's managing all the resources on the computer. Your computer, whether it be a phone or a laptop or a desktop or whatever else, it has many different resources. It has a CPU, the central processing unit, which is doing all of the work. It has some amount of memory, it has some amount of disk space, and all of that is actually managed by your operating system. And what that means is each process that's running on the machine, whether it be your Chrome browser or whether it be an app on your phone or whether it be a Java program that you've written, each process has to request access to be able to use any of the resources on the machine. And so in Java, when you say, make me an array of size 100 where each cell can hold an integer, what actually happens is Java has to go to your operating system and say, excuse me, I would like to borrow 32 bits of RAM, because that's how much it takes to store an integer, times 100 in a contiguous block, which I'm going to call my array. And then the operating system says, okay, sure, you can have that much memory. We have that available. There it is. It's yours and only yours. No one else is allowed to look in that memory. And it's doing that for every application that's running. And you might say, well, what applications are running? Right now, on this computer that I'm recording this video on, there is at least PowerPoint running, which is showing the slide presentation. Okay, it's actually Google Slides, but same difference. There's a Chrome web browser running. There is the process that's recording my audio. There's a process that's recording my video. There are other processes that are updating the clock, running other services, connecting out to the network and updating information. There's all this stuff that's running all the time. And each of those processes is code that somebody wrote in Java, in C Sharp, in some other language that's running on the machine that is requesting resources from the operating system. And it's possible that at times the operating system has to say no. If everybody keeps requesting memory, you have a physical amount of memory in your machine. When you bought your laptop, maybe it came with 8 gigs of RAM or 16 gigs of RAM, or maybe you're really fancy and you've got 128 gigs of RAM. However much you have, it's a set number. And that means that that's the most amount of RAM or memory that can be accessed by the programs. So if a Java program says, I need an array that can hold 1.8 billion integers, then that's going to allocate 1.8 billion times 32 bits of RAM, which is a whole lot of RAM. And the Java process may be able to get that, or it may simply be told, no, you can't have it. We don't have that memory. So that's what your operating system is doing all day, is it's managing that. With regard to the threading that we're talking about here, we're mostly dealing with the central processing unit. Again, when you bought your machine, you bought a specific CPU. Either it's probably made by Intel or AMD, or it might be an ARM processor, depending on the type of machine that you bought. Either way, whoever made it, it has a set frequency at which it runs. That's how fast it can process instructions, and it has a number of cores. If you bought a machine 15 years ago, it had a single core because that's all we knew how to do. And then over time, we got to the point where you could make a 2 core, a 4 core, an 8 core processor. They now make processors that have hundreds of cores. So the CPU has a set amount of capability. It can do 3 gigahertz of processing, which means it can do about 3 billion operations a second. An operation would be add these two numbers together. And so when your Java program says, I need to add X and Y as two variables, what really has to happen is it tells the CPU, load the value of X into a register. It tells the CPU, load the value of Y into a register. And then it tells the CPU, perform the operation add on register 1 and register 2 and put the result in register 3. And then it does a fetch to get the answer back out of register 3. So that's insert, add, and fetch, about 4 operations to add two numbers if they were stored in variables. And the CPU has a certain amount of capability, about 3 billion operations a second. And it's not just your Java program that's asking for stuff. Chrome and Firefox and Safari and your PowerPoint presentation and your recording videos and all these other things are asking for resources as well. And the operating system is deciding who gets to go when. So right now, there is a fight going on behind the covers in my machine where the thing that's recording my audio and the thing that's recording my video are having to compete for the processor. And so at times, sometimes it may get behind. It may be that right now the video processor, the thing that's recording the video, is a little bit behind real time. And that's it'll eventually catch up, and the software is such that it'll stitch the video back together again, hopefully. But that is the reality of the world. All of these processes are asking for stuff continuously, and there are hundreds, if not thousands, of threads that are running at any given moment. Okay, so that is to say, you don't get a vote. You, the coder, do not get a vote in what order things will be executed once you say that they're threaded. It's up to the operating system to make that decision. And it will try to be fair. That's a part of being an operating system, is that you don't want to give all the resources to one process because that would be unfair. So it tries to be fair and spread them around. But as a result, it's unpredictable at exactly what order things are going to run in when you have a multi-threaded environment. So a very important detail is if you run a multi-threaded process multiple times, you may very well get different output. Okay, so let's take another example here. In this case, what we're going to do is we're going to make 100 dogs and we're going to have a dog race. So we make an array of dogs, each of which will hold one dog, and we have 100 slots. Then we're going to make an array of threads that has 100 slots. And then I'm going to say for 0 to 100, make me a new dog, put it in the dog array, make me a new thread, put it in the thread array, and use the dog that you just created as that thread. This will create 100 threads, and each thread has a dog. And each dog has that run method that has the block of code that tells it to print out. And then I'm going to simply say for I equals 0, I less than 100, start all the threads. This will immediately start thread. So we have the main thread. It'll start thread 1, thread 2, thread 3, 4, 5, 6, 7, 8, 9. And at the same moment, there will be 101 threads running, all of which are trying to execute the dog. Now, do I have 101 cores in my processor? The answer is no, I don't. I think I have 16 cores in this particular laptop. So how does that actually work? Well, this is what the process is going to look like. You're going to get output from various dogs, and each time you run it, it's going to be slightly different. But you can see here, I'm getting a little bit of dog 35, then I'm getting a little bit of dog 11, then I'm getting a little bit of dog 95, then I'm back to 35, a little bit more from 95. It's all very, very random as to what I'm getting. And that's because each thread will have a life cycle. So let's start and look at where we are. In the beginning, the thread is created. This is when I say thread, my thread equals new thread, and I tell it which dog it's going to be. That's a new thread. There are two possibilities that that thread can go to. If I tell it to start, it's going to go into this box. If I tell it to stop, the thread is dead and it'll be removed by the garbage collector. All right, so assuming I tell it to start, what's going to happen is the thread is either going to be in the state of runnable or running. So when we begin, the thread is going to be runnable, which means it's not actually running right now, but thumbs up, we're ready to go. In the case of this particular dog that we've written, there's nothing that would stop this dog. It's simply supposed to count from 0 to 1,000, which is something it can do without having to rely on anybody else. So at the moment we create this thread, Java is going to deem that the thread is runnable. So all 100 threads will be created and they will all be deemed runnable. So now what's going to happen is the operating system is going to say, okay, I have 16 actual cores that I can process a thread on. Assuming nothing else is going on in the laptop, which is never the case, but assuming for a moment nothing else is going on, likely what's going to happen is the operating system, Windows, is going to take threads 1 through 16 and it's going to switch each of them from runnable to running by handing each of them a CPU core. So thread 1 is handed core 1, thread 2 is handed core 2, and they're allowed to start executing. So dog 0 will then start saying, I'm at position 0, I'm at position 1, I'm at position 2, I'm at position 3, and all that's executing on core 1. Meanwhile, on core 2, Thread dog number one is executing there, and he's saying I'm at 1, 2, 3, 4, 5. And likewise, the same for dog 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, or 15 because we counted zero. So all of them get stuck into a running state and they're each handed to a processor. At the same time, dog 17 is still in a runnable state, but he's not actually able to run right now because, well, there's no available core. So 17, 18, 19, all the way up to 100 are going to be sitting there in a runnable state. The first 16 are going to be counting 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And at some point, the operating system is going to go, okay, cool. I get that you can still keep running, but right now I'm going to stop you and I'm going to ask somebody else to be allowed to run. So rather than just letting those 16 run to completion, because it doesn't know how long that's going to take, it's going to let them run for a moment and then it's going to pause those 16, put them back into a runnable state, and then it's going to grab 17 through 31 and it's going to put them into a running state and hand them the CPUs. It's going to let them run for a while, then it's going to yank them off the CPUs and grab the next 17 and put them on, or the next 16, and keep doing that until it gets to the end of the queue. Then it says, okay, let's go back to thread 1 through 17 and let's put them back on the CPU and let them run for a while again. And maybe some of them finish this time around, at which point it marks them as dead because they've completed what they need to do. So the process of going from runnable to running is simply dictated by the operating system. It decides how long to let each thing run. There are some things that will cause the operating system to immediately stop you. If you're a thread and in the middle of the thread, you're waiting for the user to type something in, then immediately it's going to say this thread is blocked because it's waiting on something else. It's waiting on the user to type. And as we said before, compared to 3 billion operations a second, the user is a really slow typer. So, in what it's going to do is it's going to say, this thread is blocked. So, I'm going to put it into a not runnable state, a blocked state, and I'm going to leave it up here in the queue until it has successfully cleared its blockage, i.e., the user has typed in and hit enter, which may be thousands or millions of seconds, or sorry, of cycles on the CPU. And during that time, it will prioritize all the other people. Think about this like you're in a grocery store and there's one person running the checkout and you've got 100 people that suddenly need to check out. Really, what it's doing is there's somebody at the front of the line going, okay, you go. And it's probably trying to pick the people with the smallest amount of groceries because you can get them in and out really quickly. The people who have some big, bulky cart, okay, we're going to leave them for a minute and we'll work on everybody else. But the process of doing this is dealt with in a part of the operating system called the kernel. And very specifically, this is the scheduler. This is one of the most complex pieces of code that exists, is the scheduler in both Windows, Linux, and all the other operating systems. It's really, really difficult to do this in a fair way, and it's a really complicated block of code. But it is just code. It's code that somebody sat down and wrote and decided exactly how they're going to handle this and who's going to get priority and how we're going to do that. Every now and again, like every couple of years, there's a breakthrough and we find some new clever algorithm that's a little bit more efficient at doing stuff. It's also the case that for some types of jobs, you can schedule differently because you may want to do something in a particular order. You might want to give priority to some types of processes. So, this is all part of a class that you'll probably later take called operating systems, where you'll learn all about how the scheduler works and what it's doing in the backend. But from the perspective of Java, what you need to get out of this is once a thread is handed to the operating system and it's in a start, it's up to the operating system to decide when it actually executes. And it's unpredictable from the perspective of the end user as to exactly which one is going to run. In all the scenarios I've discussed here, I've been assuming your Java program is the only thing running on the machine, and that is never the case. There are thousands of other processes that are all running here on the machine at the same time. Okay, so here's a picture of how a multi-threaded program works. You've got your main method, which is your main thread, and then it tells you to start three other threads in this example, thread A, B, and C. And down here, what we have is an indication that we're going to switch back and forth between them. If you take the example that there's only one available core, When you have a multi-threaded Java program, it's all going to execute on that core. And literally what's going to happen is it's going to give thread A a little bit of time, then thread B, then C, then A, then C, then B, then A, then B, then A, then B, then C, in whatever order it decides is appropriate. And it's going to switch back and forth between them as fast as it possibly can. So we've mentioned this is what an operating system is. Basically, it manages all of your resources. We've mentioned that memory is one of those resources. We've talked about the different processes. There is a thing in Windows called the Task Manager, which you can open up, and it will show you all of the processes, all of the threads that are running, how many CPUs you have, how much each of them is working, how busy everything is, and all of that. There's equivalent programs on Mac, there's equivalent programs on your phone that'll do the same thing. And then this is just talking about the same thing that I described, where things are passed back and forth. Processes are executed in whatever order it can in order to get them done. Um, as I mentioned, waiting for the user is an example of where you get blocked. But just as an aside, even accessing memory will block the process because if it has to pull something out of memory, that takes a couple of cycles to do that. And while it's doing that, it can be working on some other process. Likewise, network sockets, they're really slow if you're waiting for something from the internet or waiting for a file. All of those are going to cause your process to get, or your thread to get blocked. All right. So, when would we use threads? Well, in general, there is a problem that you have at any large um, scale website. So if you take something like an Amazon or another big e-commerce site, or even if you take something like a social media site like your Snapchat, your Twitter, or any of the social medias, each of them has a problem, which is that the users don't all come in a nice, even, steady pace throughout the day. There are times where it's just much more busy than other times. For example, in Twitter, as a random example, the busiest moment of the year is at midnight in each time zone on December 31st. That's because everybody tweets Happy New Year. And that's millions and millions of people that are all doing the same thing at the same moment. And that's really busy for the servers. So the issue with this is if you're building a large scale application, you have to know what the busiest moment is going to look like, and you have to have enough servers to deal with that busiest moment, which is very, very expensive. So think about it this way. How many people are going to place an order at once on some large e-commerce site? The whole world is possible, right? So if you assume that this e-commerce site is used all over the world, the question is, what's the peak going to be? What's the maximum number of orders that you're going to have? Well, it probably depends on the time of day because it turns out I'm usually asleep at 4 o'clock in the morning. I'm probably not making very many orders then. But at 7 o'clock and 8 o'clock, when people start waking up, you're going to start seeing an increase. And maybe by noon, when everybody's on lunch break, they all go on their phone and start ordering stuff. And so the peak may be at noon, or it may be at 4 o'clock in the evening, or it may be at 8 o'clock. And you may end up with a graph that looks something like this, where throughout the night there's not a lot going on, but then as the day goes on, it gets higher and higher, and it actually peaks in this case at about 10 or 11 o'clock. This is a random example. Certainly, it could be different depending on what you're selling. If you're selling tickets to a concert, then in reality, it's going to be no traffic, and then all the traffic at the moment you release the tickets, and then no traffic after you're done. It's just going to be this huge spike that's going to hit all at once. And so different applications will have different graphs that look like this. And a real job that people have to do is to figure out how to make this work. If you only have a fixed amount of servers, even if you're using cloud services, you have a budget as to how many resources you can use at any given moment. You're going to have to figure out how to even out that graph so that it's constantly working, but you're not getting killed at the moment when everybody is hitting all at once. You don't want to have it to the point where somebody is trying to place an order and they get an error, because that's not a good experience for anybody. No matter what, you want to get the order, but you may not be able to process it immediately. And so that's where we get the idea of being able to smooth out peaks in a graph. And this is typically done by introducing a queue into the process. So this is how most large sites that you see on the internet, most large applications that you might use on your phone deal with this peak load problem. Instead of immediately doing what the user tells them to do, what they really do is they take what the user asks them to do and they put it in a queue. And then they keep doing that for all of the requests that are coming in from all over the world. So let's take the example of an e-commerce site where I'm buying things. I go online, I pick out the item that I want, I put in my credit card, and I hit buy. At that moment, it doesn't actually do anything. It simply records the fact that user Enda Sullivan has asked to purchase whatever it is that Enda Sullivan has asked to purchase, and it puts that into a queue. And then separately, there is a process that runs in the background that checks the queue and sees if there's any work that needs to be done. The first step that may need to happen after you place an order on an e-commerce site is it needs to charge you for that amount. And in reality, that means it's going to have to make a connection to a bank and verify a credit card and make sure that that goes through and actually initiate the funds transfer. And all of that takes time. So it doesn't do that while I'm typing it in on the app. It might tell you that it validated the card right then, and it may be that they do it right there and then, but most of the time they pre-validate the card when you first put it into the app. Usually you have to put it in before you can place an order. And so at that moment, the process deals with that. But now that there is an actual order, it still needs to actually charge the card. So my order got put into a queue, and then what's called a worker process comes along and grabs the order, and it actually charges the credit card. It records in the order that it's now paid, and it puts it back into the queue for later processing. At some point, somebody's going to have to go into the warehouse and actually pull my item, put it in a box, and mail it to me. So, what happens there is when a worker, a literal person in this case, is available in the warehouse, they press a button in the computer, it grabs the queue out of, or grabs the order out of the queue, it marks that that user is now pulling that order. The user goes and fetches it, puts it in a box, and slaps the label on it, and then they mark the fact that the order has been processed. And then it goes back into the queue again and it waits because it actually has to be delivered to me to be considered done. So it's going to sit there and wait until a truck picks it up and brings it to my house and drops it on my door, and they take a picture of it or whatever it is that they're going to do. So the order sits in this nebulous queue thing, and different processes, which are sometimes human and are sometimes software, reach into the queue, look for things that need to be done, and do them. And the advantage of doing stuff in this way, rather than doing it all at the moment when you press the button, is if you think about it, it wouldn't work at all if that's how it worked. If I go into Amazon, as an example, and I say I want to order a new pair of shoes, and I put it in there, and when I hit go, I actually have to wait for it to charge the credit card, have somebody in the warehouse go find those shoes, put them in a box, print out a label, and actually deliver it. And until then, it doesn't actually say it's done in the app. Yeah, that's a terrible user experience. So it tells me it's done the moment I hit the order, and then they just keep track of it in the background as it steps through each of the steps. This allows them to have a specific amount of work at any given moment. So the orders can go into the queue, and the queue may get backlogged. There may be thousands or millions of orders sitting in the queue that need to be worked on. They can control how fast they're charging the credit cards by having a set number of worker processes that are each charging one credit card. So basically, you have a machine that's running some Java code that has an infinite loop. And the loop pretty much says, is there an order in the queue? If there is, it grabs the order, it charges the card, whatever that looks like, and then it marks the order as done and puts it back into the queue. And meanwhile, there's another computer sitting next to it that is also asking the queue, is there currently an order? And there's another computer sitting next to that that's also asking the queue. And as a matter of fact, in the case of Amazon, there may be thousands, if not millions, of computers that are all running that same code. And so the time that you sit in the queue before it actually gets to you is determined by how many different working machines they have that are doing this task and how many orders are in the queue. But the nice thing is, the amount of work that they have to do never changes. The amount of work is however many machines they have running the queuing, the charging credit card process. And if that number is to be 700,000, then that number is 700,000. And whether there's 5 orders coming in or 5 billion orders coming in, the 700,000 will get to each order whenever they get to it. If they find out that the queue is always growing and they're not able to process all of the orders per day, then they need to add more working machines that are actually able to process queues. And so they stand up more machines. If they find that there's no queue and it's able to process everything instantly, then maybe they have too many resources and it's costing them too much money to keep all those machines going, so they can shut down some of them. And in actuality, a common thing that people will have is that the number of working processes on this grows and shrinks throughout the day. At 4 o'clock in the morning, when there's little or no orders, they may condense down to a much smaller number of workers because they don't need all the workers. And then at 9 o'clock, when everybody wakes up, they grow the pool again. And this is a dynamic workload which can be done in cloud computing. You just have a process that can be started and stopped whenever you need it. Okay, so let's take a look at how this would all look in code. So here we have an order class, and it has, the normal things like it has an order ID and a description and a quantity and a total and all those things that you would expect. And you've got some kind of a constructor that takes in, the description, the quantity, the total, and it sets the attributes in the class. Then we have a get ID, which just tells us my ID, that's a getter, and we have a toString so I can print out what the order looks like. Okay, so nothing about this is threaded, this is just an order object. It keeps track of an order for one item. All right, so inside of that, let's take a look at a queue object that we might have. So this is class order queue, and it has an array list of orders. And we basically have the ability to add an order to the queue. We have a check, is the queue currently empty? And we have a get next order. Okay, so again, nothing about this is threaded. This is just an array list that's being used to keep track of all the orders. So as an order comes in, you on your UI that allows people to make an order, you simply press add order and you put the new order into the queue. And it keeps track of the queue in this array list for me. All right, easy so far. So now we have the worker that's actually doing the process to process the order. So again, another class. This one implements runnable because we're going to want more than one of these running. So we tell it, okay, it's got an order queue. That was the thing we just looked at a moment ago. And it has a constructor that sets up the order queue. All right, then we have a process order method and we have a run. The process order is what actually does the work. And obviously, there'd be code in here that charges the credit card, routes the order to the warehouse, and has the warehouse dispatch the order. All of that code I'm not writing. I'm just saying, here are comments that somebody would write that code someday. The run part of it says, while the queue is not empty, then process an order, sleep for a little bit, and then do it all again. So effectively, this worker will check, is the queue empty? Nope. Okay, grab an order, process it, and then go to sleep for a half a second. When you wake back up, is the queue empty? No. Okay, grab one. Now you might say, why are we sleeping for half a second? Well, imagine if there's nothing in the queue. Then this would say, is there anything in the queue? 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 3 billion times a second. And in reality, there aren't that many things coming into the queue. You're just spending a whole lot of CPU time working on something that's not really doing anything. So usually you'd have some kind of a sleep where it just stops for a moment and lets somebody else into the queue. So it doesn't have to be there, but that's generally what you would do in a worker process. All right. So in this example, you could instantiate as many queue workers as you want. Overnight from 3 to 6, maybe there's 50 queue runners. At peak, you might have 50,000 of them running. Notice that they're all asleep after processing an order. Again, common tactic, so it's not just going crazy. And this is something you could adjust as you need to as well. So keep in mind that all of this is a trade off between how fast each order is processed and how much work you have to do at peak. By having more workers, you will have more capability to process things. It costs more to do that, and the orders get handled faster. With less workers, you will have delays in processing the orders, but it's cheaper. And so you, as a business owner, get to decide where you want that needle to be exactly. Do you want faster order processing, or do you want a lower overall cost? And in reality, there's real costs to all of these. So these are real decisions people actually have to make. All right. So, an important detail about everything that we just looked at is that the example we just did is not thread safe. So, going back to the code that we just looked at, where we have this queue worker, here is a scenario that could happen. Because this simply says, is the queue empty? And then it grabs and orders or processes the next order. What would happen if two processes at exactly the same moment both asked, is the queue empty? And imagine there's just one order in the queue at the moment. So two processes wake up. They both say, is the queue empty? They're both told no, because there's one process or there's one order sitting there waiting to go. So they both say, okay, get next order. And both processes at the same time reach into the queue and ask for the next order. Well, they'll both get the order because they both see the same order. So they will then both start processing the order, which means they'll both charge the credit card and they'll both dispatch a TV to that user, which is really not ideal because the user only ordered one. There was only one order. It's a bug in the software that both of them were able to get the order at the same time. This is an example of being non-thread safe. Array lists, which is what I used in this queue, are not considered thread safe. And what that means is more than one person can pull something out of the array list at the same moment. And that's really not very desirable. So when you're dealing with a multi-threaded system, something you always have to ask yourself is, could two threads do something at the same moment? Here's a fun example. Let's imagine that you have two debit cards to your bank account. You, for whatever reason, tell the bank that you lost your ATM card. They give you a new one. So now you have your old one and your new one. You get a friend. You ask your friend to go to an ATM, and you go to an ATM at the same moment. You call each other on the phone. You say 3, 2, 1, and you both put your card into the ATM. You tell your friend your PIN number, which this is a terrible idea for many reasons, and then you both type in your PIN number at the same time on the ATMs in two different locations. You ask the ATM, what's your balance? And it says you have $100 in your checking account. So you both type in withdraw from checking $100. And then you say, at the same moment, we're going to hit enter. 3, 2, 1, go. And so you both hit enter. What's going to happen? Both ATMs are going to ask your bank, does he currently have $100 in his account? Yes. Both ATMs are going to dispense $100. And then you're both going to walk away with $200, even though you only ever had $100 in the account. This seems like a great hack. Infinite money. All you need is infinite ATM cards. The answer is this doesn't work. The banks have long since thought through this. But this would be an example of a thread safe problem. The issue here is that both people, both ATMs, at the same moment asked the account, is there $100? And they were both told yes. But then they were both able to dispense the $100 because they both thought there was $100 in the account. This doesn't work in the real world because what actually happens is if you both put the ATM card in and you both type the PIN, one will get what's called a lock on the account. The other one will give you an error and say, sorry, your account's not available right now. And that's because they've implemented a thread safe solution. They've made it such that both sides can't possibly get to the same data and change it at the same time. Everything with threads has this problem, and it's going to be a very big issue that you're going to have to deal with in life when you write multi threaded code. And this is why I say this is not a trivial topic. Imagine you write an application that writes to a file and it does it in a thread. What happens if two threads attempt to write to the file at the same moment? Who wins? What data ends up in the file? Is it the data from thread 1 or the data from thread 2 or a mixture of the two? That's a real problem because most likely you're probably just going to corrupt the file. So again, you can't just do things in threads. If they're both accessing the same information, you have to be very careful about making sure that the way that you access that information is such that you don't create problems. So back to our e-commerce example here, both people are making requests both worker processes are making requests to work on the order at the same moment. What needs to happen is it randomly decides which one is going to get it. It needs to give that one the lock, and then it needs to prevent the other one from touching that order. That's what needs to actually happen. And so the way that this is done is you need to use a thread safe structure. Array lists, as I mentioned, are not thread safe. And what thread safe means is that it implements an atomic way of accessing the data. That means that if one person is allowed in to make changes, no one else is allowed to make changes at the same time. So effectively, what would happen in our multi-threaded application, if we had done this with a thread-safe data structure, is that when the first worker grabbed the order, it would have locked the order such that no one else can touch it. And as a matter of fact, any other process that tries to reach in and touch that order would get told no, and they would go to sleep wake up and pick the next order instead. And this is called thread safe. So the way that you do this is through a keyword called synchronize. And synchronized is used in multiple different ways. You can use it in a method, you can use it around a block of code, or you can use it for specific types of data types that are listed as being thread safe. So there is a type in Java called collections.synchronized which is very similar to an array list. And the way that it's used here is this is my queue process or my queue object again. So I have my list order, which is where I'm keeping my orders. But instead of saying list order equals new array list or array list order equals new array list, I'm instead saying list order equals collections.synchronize list new array list. This makes it so that only one thread at a time can access each cell. Now, from the perspective of getting stuff done as fast as possible, this is bad because it means that each cell can only be accessed by one thread. If you have a job where each thread is trying to look in each cell, that's not going to work anymore. They're all going to be queued and only one is going to be allowed in at any given moment. So it's going to break the ability for there to be multiple people jumping in all at once. But the benefit is it stops the issue that I just described, where two things could conceivably grab the same data at the same moment. Okay, so likewise, our add order, our get next order, and our is empty are all going to have the word synchronized around them. And what this again means is that at any given moment, only one add order can be happening. This is important because if multiple add orders were allowed to happen at the same moment, what would happen is the first one would get written into cell one, and the next one would also get written into cell one. So this prevents that from happening. It makes it so that each time the add happens, only one person is allowed to add to it at a given moment. So again, there's a cost benefit analysis here. Do you care that it is safe and that only one thing is going in at a time? If the answer is yes, then the cost of that is that you're not able to parallelize as much. So this synchronized has a downside in that it prevents multiple people from calling add order or get next order or is empty even at the same moment. They all have to be answered one at a time. But it guarantees you don't have the previous example. All right, updating the queue worker, this is the thing that's actually doing the work. You notice that very little here actually changed. I'm still able to just say get next order. I don't have to care that it's using a synchronized data structure. This is my run process, which is dealing with my threading here for my queue worker. And so it doesn't really care that we're using the synchronized one. It works the same either way, except it doesn't work the same. Sorry, for the code on this side looks the same either way, but the way it's working is quite different because of the synchronized data structure. And then here's my example driver to run all of this. This is my e-commerce driver. So I set up an order queue and then I say add an order, new order of milk, quantity 2 for a total of 540, add an order, new order for cheese, add a new order for bread, add a new order for apples. So there are 4 things in the queue. And then I've started 2 workers which are both threads, and I run start. And you can see worker 2 is processing order 1, worker 1 is processing order 1000, worker 1 is processing order 1002. You notice they're not necessarily being done in order, but they're all getting done. And then it tells me, by the way, we're done with all of them. So this is how the process would work. In reality, you'd have however many workers you need here, and they would be in a loop to start them off, much like we did before. All right. So the important detail here is that if you're using any data structures inside of Java and you're doing it with threads, you're going to want to go look at the Oracle documentation. Every Oracle is the owner of Java, and so there is documentation for every class out there. This is the documentation for ArrayList, and I grant you this is in very small font, but notice that class implementation is not synchronized. That's telling you you can't use this in a thread safe way. So you need to actually read the documentation, especially when you're doing multi-threading. All right, so the next topic is the keyword join. If you have a bunch of work that you want to get done, a fun thing you can do is you can break the work up into smaller chunks, make multiple threads, and have each thread do a part of the work. So, for example, imagine I have a huge array with 10 billion cells, and I need to look through that array for a particular value. Maybe what I do is I write 10 threads, and each of them does 1 billion cells. If I have a 10 core processor, it'll do it in 1/10 the time, give or take. So this is great, but of course, as each thread completes, I need to get the answer back from that thread. And the question is, well, how do you know that the thread is complete? And that's where you get the keyword join. So effectively, what join does is it waits until the thread is complete. And so imagine we have this class here. This is our search array class. It implements runnable and it takes in, in its constructor here, it takes in an array. It takes in the thing we're looking for, the needle in the haystack, and it takes in a first and a last index, which is the part of the array that this thread is going to look through. And so the run method is simply, from start to end, look at each of those, and if you find it, print it out. Great. So this is my runnable thread. So here in main, I have something that's generating a big array with a whole bunch of numbers in them. And I'm going to make two of the search array objects, and I'm going to start the threads and have them start running. So T1 start, T2 start. So once these are started, I need to know when they're done. And I do that by saying T1.join. What T1.join does is this line of code will not proceed until thread 1 completes. And what I mean by complete is it has to actually finish whatever work is in the run method, or be exited or returned from. But either way, it has to complete. So this line of code will wait forever until thread 1 completes. So if you have an infinite loop in thread 1, this is never going to happen. But in this case, we're going to look through those cells and it's going to tell me, okay, thread 1 is now done. This is going to wait for thread 2 to finish and it's going to tell me thread 2 is done. And at this point, I know both of my threads are done. So I know they both looked through their half of the array. And now I can tell whether we actually got an answer back or not. All right, so this is a trivial example. You will use join all the time. It's possible to access information on the internet in your code. We saw that in the last class where we had sockets. So the problem with the internet is that it can be quite slow. You may have Wi Fi or network delays. You have a server that may be too busy to answer your request right now, or it may just be a really far away server. If you're asking for something in Australia, the speed of light is still going to take a moment to get all the way from there to here. So typically, anytime you ask for something like data from the internet, you're actually going to do that inside of a thread. And that thread is going to run and it's going to wait until it gets the answer back. So effectively, what you're going to do is you're going to say, go to the internet and get me this information. And then you're going to say join to wait for that thread to come back. So you can ask for many pieces of information simultaneously in separate threads, and then you just have a whole bunch of joins that are waiting for them to come back. As a matter of fact, this is how your web browser actually does things. When you type in a URL into the web browser, it's got a whole bunch of information it's got to go get from the various sites to render that. Especially if the web page has a lot of images or videos or other stuff in it, each of those images have to actually be requested separately. So what happens is it creates a whole bunch of threads. It sends each thread out to find one piece of information, and then it sits there and it waits until they come back. And then as they come back, it renders just that piece of information. Which is why, if you've ever noticed, if you render a web page that has a bunch of images, they kind of just appear randomly on the screen in some order. And that's because that's the order that the threads completed and it got that information back. Okay, so each thread has a bunch of methods that you can use. We have start, we have run, we have sleep, we have yield, and we have join. So we've seen start, that's how you begin a thread, and we've seen join, that's how you wait for the thread to end. Yield is something you can do where you can tell the thread to just stop running for a moment and let other threads run. If you have something that's a low priority, you can ask the thread to yield. Likewise, sleep is so that the thread will do nothing. And it immediately puts the thread into a blocked state for that amount of time. And then at the end of the time, it puts it back into a runnable state so that effectively the CPU will be handed to somebody else from the operating system. So these are just some of them. There's also an is alive. You can check if a thread is still running. Okay, so a couple of last thoughts that you should talk about. First up, we have race conditions. So this is very similar to what I was discussing with the bank account, where you've got two people with their ATM cards making a withdrawal at the same moment. The same thing can happen when you're selling seats, whether it be to a concert or an airplane or a train or whatever you're selling seats to. They all have the same issue, which is that effectively you can have circumstances where multiple people are trying to buy the same seat at the same time. And it's very important that you only give the seat to one person. You can't sell it twice because otherwise you're going to have all kinds of problems. So effectively, what you're going to do is you're going to say, is the seat available? If it is available, then you're going to make it invisible to everybody else, and then you're going to write that they bought that seat. And so what you're going to do is you're going to declare that this whole area is called the critical area. And what that means is once you start this block of code, you must complete this block of code before anyone else is allowed to look at this seat. And that's what that synchronized keyword is all about. It's basically saying once you start this, no one else is allowed to mess with it. That block of code or that item in the array list or that item that you have cannot be messed with by anybody else until this thread is completed with this task. So to prevent race conditions, each thread must complete its critical code section before any other thread is allowed to enter that same critical code section. And this is done with the synchronized keyword. And again, there are real world trade offs with this, which is that effectively, if you've ever bought a ticket to a concert, you know typically what happens, especially if it's a concert that's very popular. You go to the website and you say reserve ticket, and it says you have 1 minute to complete this order, or I'm going to release the seat. Effectively, what's happened is your thread has grabbed that seat, and for the next minute, it's going to hold on to that seat. Either within that minute, you need to secure it by actually paying for it, or it's going to release it and allow the next thread to possibly get the seat. And so that's what's happening in the real world, is that it's actually sitting there waiting on a synchronized block of code to complete, to mark that area as done. So any method can be marked as synchronized. Again, public static synchronized void do it. This code is synchronized, which means that only one thread can execute this method at a time. This greatly reduces the ability to parallelize things, but it fixes your race condition issue. All right, and then the last topic to talk about in threading, and again, we're breezing through these are very high level views, are deadlock. So if you imagine a circumstance where you have two resources, where you have one thread that grabbed one resource and it's waiting on the other resource to be available, but at the same time, another thread grabbed the second resource and is waiting on the first one, they're never going to be able to solve this problem. So an example of this might be, I need the network and I need the disk. So I grabbed the network, and we're presuming in this example only one person can be on the network at a time, and I'm now waiting on the disk. Meanwhile, another process needs the disk and the network. So it grabs the disk and it's waiting on the network. Assuming that these are both synchronized, we're in deadlock. We're never going to be able to solve this problem. Neither of us is ever going to complete because we're waiting on the other thing, and the thing we're waiting on is never going to become available because we are locking it. This is a real thing that can happen in code, and it's very difficult to deal with. In the example I gave where you've got two threads, it's not too bad. You could see that that has happened possibly, but imagine a circumstance where you've got a circle of 50 different threads. Thread 1 has item 1 and needs item 2. Thread 2 has item 2 and needs item 3. Thread 3 has item 3 and needs item 4, all the way around until you get to thread 50, which has item 50 and needs item 1. Now it's much harder to notice because it's a circle and it's many, many threads that are all working together to create this deadlock. And in reality, what this means is your program is locked up and it will never move forward. You've maybe seen this happen in a program where you did something unusual and the program just locks up. It's possibly because the program has reached a deadlock condition. It should never happen if the coder was good, but it's certainly possible. It especially happens when you've got resources that are finite that everybody is working on. So, this is a very difficult problem to solve. It's very difficult to notice that it's happened, and it's very difficult to solve. So, this is one of the big problems that you have to deal with when you're dealing with multi threading. So, in this set of slides and in this lecture, we've talked about threads. The simplest part of this is creating a thread. It's basically just implement runnable, and you have a run method that has some code in it. Then you make a thread, you give it an object, and you call start on the thread. That's really all that we learned about new code in here. We mentioned the join allows you to wait for a thread to finish, and then we talked about all the problems that this creates, which include deadlock, race conditions, and also the need to synchronize blocks of code to make sure only one person is working on it. Again, this is a very high level view of multi threading. but it is enough for you to be able to go out and do stuff. You're probably going to make lots of mistakes where you're going to accidentally create non thread safe code because you're not going to naturally think about it. But you have to start training yourself to ask questions like, could two threads do the same thing at the same moment? That's a really important question. So, this is multi threading, which is one way to do multiprocessing in Java. There is a whole other way, which is an older way that isn't really used very often anymore, which is called multiprocess. So, what's the difference between a process and a thread? A thread is a part of a process. A process is the big thing. So, Chrome is a process, but each window or each tab in Chrome is usually a separate thread, at least one thread, often many. Um, so a process is a big application that you run. If you think of it on your phone, it's an app. Any app that you execute is going to be a process, and it may be made up of many different threads. So that's the distinction between the two. There is a way to do multiprocessing in Java that's called fork join pools. And again, it's an older way of doing things where you're using processes instead of threads. It's still viable, you can still use it, but it's not something we're going to teach in this course. We used to teach it, but we've actually removed it out of the course because it's not really very practical anymore. Most everybody is going to do it with multi-threading. So if you're interested, certainly look up the Wikipedia article on fork join pools or look at the Java documentation and you can see how to do that. But for the purposes of this class, we're not going to cover it. We're not going to ask you questions about it. We just want you to know that it's not the only way to do things. It's just that most everybody today does multiprocessing with multi-threading. So that completes today's lecture, and I will see you guys in the next lecture when we talk about data structures. See you then.